Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing bedtime astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Okay, let's unpack this. We often frame the universe as, this enormous, immutable backdrop, something so ancient and vast that it seems entirely static over the span of a human lifetime. We look up, and the stars. They're pretty much where they were for our great-grandparents, right?
Right. That's the common perception. Fixed, unchanging.
But today, we're diving into the study of a single object that, violently defies that expectation. An object whose changes are so rapid, they can actually be measured, tracked, observed over just 130 years.
And it's those dramatic, visible shifts, these objects evolving within our observational record, that really force us to challenge those underlying assumptions. We think of stellar evolution in millions, billions of years. But here, we have a real-time lab, relatively speaking, showing change over a single century.
Exactly. We are looking at the stunning planetary nebula known officially as IC418, but you probably know it better by its nickname, the Spirograph Nebula.
Ah, yes, the Spirograph. It's a great name.
Named for those complex, intricate looping structures the Hubble Space Telescope captured so beautifully. It really does look like something made with that old geometric toy.
And that nickname's important, I think. It grounds the science in something, familiar and beautiful. It emphasizes this isn't just some distant, fuzzy smudge. It's dynamic, caught right in the act of its final transformation.
Cosmic change on a timescale we can actually grasp.
Precisely.
So our mission today is built around this fascinating study published in Astrophysical Journal Letters. The team accomplished something pretty remarkable. They stitched together this almost unbroken 130-year lineage of observations for IC418.
A huge undertaking.
They did this to track the star's death throes and specifically to figure out what its, astonishingly rapid evolution means for a really fundamental question.
Which is?
How the ingredients for life, particularly carbon, get distributed throughout the galaxy.
The big one, cosmic chemistry. So it's like a detective story starting way back in the 19th century.
Ending with some pretty profound implications for how we understand astrophysics today.
Exactly.
Okay, so let's start with the basics. The object itself, IC418, where do we find it?
Right. You need to look towards the southern constellation Lepus. That's Latin for the hare. It's situated about 2,000 light years away from us.
2,000 light years, so relatively close in galactic terms, but still a long way off.
Oh, absolutely. And physically, it spans roughly 0.2 light years across.
Which sounds small, maybe, but that's...
Well, it's about 12 trillion miles, give or take, so not insignificant.
Okay, yeah, definitely not small.
But from Earth, its apparent size is quite compact. It shines at about magnitude +9.
Meaning you'd need a telescope.
Oh, yes. Definitely not naked eye. And it appears about 18 arc seconds across in the sky. Think roughly the size of Jupiter through a decent backyard telescope when it's looking particularly large.
Got it. Now we have to pause on the name planetary nebula. It's famously confusing, right? Because they have absolutely nothing to do with planets.
Nothing at all. It's one of those historical quirks. The name stuck from when astronomers like William Herschel first saw them. Through their early, less powerful telescopes, these objects looked like round, ghostly disks, kind of like the faint appearance of Uranus or Neptune.
The known planets at the time.
Exactly. They didn't have the resolution to see the structure, just these fuzzy, planet-like shapes. So the name stuck, Planetary Nebula.
But they're actually the spectacular final breaths of a star, aren't they?
That's right. It happens when a star similar to our sun runs out of fuel, expands hugely into a red giant, and then puffs off its outer layers.
Creating that glowing shell we see.
And for us, the real hook, and the reason we have this 130-year timeline, is the human story behind its discovery.
This is where Williamina Fleming comes in.
Yes. The discovery back on March 26, 1891, belongs squarely to her. She was a true pioneer of, modern data-driven astronomy.
She was Scottish-American, working at the Harvard College Observatory HCO, part of that massive Draper Catalog survey. And you really have to picture her work, right? She wasn't at a telescope eyepiece.
No, not usually. She was in a room meticulously, painstakingly examining thousands upon thousands of photographic glass plates. Huge, heavy things.
Like the world's first large-scale scientific data analyst, essentially.
You could definitely say that. Grueling work. Those plates required expert interpretation. Her role, and that of the other women known as the Harvard computers, was crucial. They classified stars based on their spectra, the patterns in their light, and spotted anything unusual, like a nebula.
And she was incredibly prolific. The notes mention she discovered 59 nebulae just during her work on that one survey.
59. Imagine. IC 418 was just one entry in a huge body of work. She was instrumental in shifting astronomy from just describing things to systematically classifying them based on physics derived from light.
Her observation in 1891 is the absolute starting point for this whole study we're discussing.
It's the anchor. Without her and the rigorous record-keeping at Harvard, we wouldn't have this baseline. We couldn't track this evolution.
And just a quick historical note, although it was later cataloged as IC 418 and sometimes misattributed, the initial credit belongs to Fleming, 1891.
Yeah.
That's our starting gun.
Absolutely key.
Okay, this is where it gets really interesting, I think. We move from historical discovery to, modern scientific detective work. You've got this object observed in the 1890s. How on earth do researchers today track its physical evolution? How do they bridge 130 years of completely different technology?
Yeah, that's the challenge. Going from someone literally describing what they saw.
Right, to photographic plates, to modern digital cameras.
Like the Hubble Space Telescope, it's what we might call forensic astronomy.
Forensic astronomy, I like that.
And IC 418 had a unique advantage. It has this almost unbroken chain of spectroscopic measurements.
Spectroscopy, breaking down the light.
Exactly. Breaking light into its component wavelengths like a rainbow to figure out temperature, speed, chemical makeup. That technique was just getting started in the 1890s, and IC 418 was an early target.
So they were pulling data from completely different eras. Visual observations, glass plates, film, digital CCDs.
Three distinct technological phases. And the trick is making sure the data from all these sources, speaks the same language, can be reliably compared.
How do you even use data from, say, 1893? You mentioned William Campbell observed a spectrum then. How is a visual description useful?
It sounds imprecise, doesn't it?
Oh.
But the key is that early astronomers, even without digital tools, were incredibly meticulous note-takers. Dr. Albert Zijlstra, one of the researchers on this recent study, pointed out that Campbell's observation was described well enough.
Well enough for what, though?
Well enough to establish a baseline. He described the visible emission lines. Crucially, their brightness relative to other known lines, like hydrogen. That relative brightness gives you a starting point, even if it's not a precise number like we get today.
So it's the relative information that matters. That's amazing. Trusting those 140-year-old notes.
It's a testament to their standards. They knew they were recording something important.
But the jump to photographic plates must have been a huge challenge, correcting for the technology itself.
That's where the forensic part really kicks in. You have to account for technological bias. An old glass plate doesn't record light linearly. The brightness depends entirely on the chemical emulsion used on that specific plate.
Ah, okay. So different plates from different times might be more sensitive to blue light or less sensitive to red.
Precisely. And a researcher today needs to know that specific sensitivity profile to figure out the star's actual energy output at different wavelengths back then.
So they had to mathematically reconstruct
What?
the chemical properties of old photoemulsions.
Essentially, yes. They model the sensitivity curves of those historical chemicals. They look at old lab notes, logbooks about atmospheric conditions, even the type of silver halide used. It's about converting a recorded density on the plate back into a physically meaningful photon count.
That is incredibly detailed work. You're part historian, part chemist, part astrophysicist.
It takes a team with diverse skills, definitely. But it's crucial to make sure the 1893 data is genuinely comparable to Hubble data from, say, 2018. The whole study hangs on getting that right.
And they focused on specific emission lines, you said, hydrogen and this doubly ionized oxygen, OII.
Yes, those were key, especially the OII lines in the blue-green part of the spectrum. And that connects back perfectly to another historical quirk, the nebulae mystery.
Ah, right, the element that never was.
Exactly. Back in the late 19th, early 20th century, astronomers kept seeing these really bright, distinct emission lines in nebulae spectra, lines they couldn't match to any element known on Earth.
So naturally, they assumed.
It must be a new element. They even gave it a name, nebulium. It was a big puzzle. Why couldn't they recreate it in the lab?
Until physics caught up.
Right. It wasn't until the 1920s, with advances in atomic physics, that Ira Bowen figured it out. It wasn't a new element at all.
It was just familiar elements acting weirdly.
Exactly. Common stuff like oxygen and nitrogen. But under the incredibly extreme conditions inside a nebula specifically, ultra-low density and intense radiation, these atoms can emit light in ways through forbidden transitions that are basically impossible to achieve in a dense Earth atmosphere.
So the light they called nebullium was actually just ionized oxygen behaving strangely because of the nebula's environment.
Precisely. And the way those oxygen atoms emit that specific light, the former nebullium signature, turns out to be extremely sensitive to the temperature and density of the nebula gas.
Ah, so tracking those specific lines over 130 years lets them track how the physical conditions inside the nebula have changed.
That's the key. They started out chasing a fictional element and ended up using that very same light signature to measure one of the fastest stellar temperature changes ever recorded.
Incredible, the science evolving alongside the observation. Okay, let's get to the core discovery. The numbers that really made the astronomical community sit up and take notice. But first, maybe just quickly remind us what's actually happening when a star like this dies. What are the death throes?
Right. It's a dramatic, but in a way beautiful process. It starts when a star, roughly like our sun, exhausts the hydrogen fuel in its core. Gravity causes the core to contract and heat up while the outer layers swell enormously. It becomes a red giant.
Sometimes swallowing its inner planets.
Potentially, yes. Then, over a relatively short period, astronomically speaking, it sheds those bloated outer layers into space. That expelled gas and dust forms the expanding, glowing shell of the planetary nebula, like IC418.
And what's left behind in the center?
The incredibly dense, hot core of the former star. It collapses down into what we call a white dwarf. Think of it as a stellar ember, compressed to about the size of Earth, but still containing maybe 60% of the star's original mass. In IC418's case, it's about 0.6 times the sun's mass.
Just glowing incredibly hot from leftover heat.
Exactly. And this whole process, this is the fate awaiting our own sun and solar system in about 5 billion years.
Right. So IC418 is showing us our future, in a way.
In a very real way.
Yeah.
Now, normally the changes in a star's temperature, especially during these later stages, happen over incredibly long timescales. Millennia. Millions of years.
We usually consider them constant over human history.
Pretty much.
Yeah.
Except here. This study gave us the first continuous century-plus look at this specific white dwarf formation phase. And the numbers are startling.
Okay, what did they find?
They determined that the central star, that white dwarf, has increased its surface temperature by a whopping 3,000 degrees Celsius since Williamina Fleming first recorded it back in 1891.
3,000 degrees Celsius in 130 years.
Yes. That breaks down to a heating rate of roughly 1,000 degrees Celsius every 40 years.
Wow. So in a single human generation, that star gets substantially hotter. You could theoretically measure the change within a working astronomer's career.
You absolutely could. We are literally watching this dying star heat up dramatically, almost in real time.
That puts astronomical change on a human scale like almost nothing else. The source material compared it to our sun's formation, right?
It did. Our sun, during its own formation phase when it was settling down, saw a similar temperature increase, maybe a few thousand degrees. But that took something like 10 million years.
10 million years. IC418 did it in 130?
It's deep time accelerated. This rapid heating happens as the star sheds its final outer layers, like throwing off a blanket, exposing the incredibly hot, contracting core underneath. As that core shrinks under gravity, its surface area gets smaller, but the energy gets concentrated, so the surface temperature just skyrockets.
Okay, that makes sense. Rapid heating as the core is revealed, but here comes the paradox, right? This is what messes with the models.
This is the kicker. While that heating is incredibly fast in human terms, the study found that this rate, this 1,000 degrees every 40 years, is actually slower than current theoretical models predict for a star like this.
Wait. It's heating up super fast, but our best physics says it should be heating up even faster.
That's the puzzle. If you take the known properties of IC418, its mass, the nebula's expansion rate, and plug them into our standard computer models of stellar evolution, those models predict an even more rapid temperature increase than what we've observed over these 130 years.
So the star is putting on the brakes somehow, compared to the theory.
Or perhaps the theory has the accelerator pushed down too hard. It suggests there's something we don't fully understand. Maybe some process is slowing the final collapse or moderating the thermal output. Could it be some residual low-level nuclear burning deeper inside than we expect? Or maybe the way the very last bits of mass are ejected affects the surface temperature profile differently.
So this slight discrepancy in speed, it points to a gap in our understanding of the physics right at the very end of a star's life.
A potentially significant gap. if we don't quite grasp the thermodynamics, the heat flow.
Then we probably don't fully grasp the chemistry either.
Right, so let's pivot to that so what question. Why does a 3,000-degree temperature difference or a slight mismatch in heating speed in a nebula 2,000 light-years away actually matter to us?
Because it connects directly to where the building blocks of life come from.
Carbon.
Carbon, exactly. This finding is crucial because these dying intermediate mass stars are the primary factories for creating and distributing elements heavier than helium back into space. And the analysis confirms IC418 is explicitly a carbon-rich nebula.
Meaning the star itself cooked up a lot of carbon inside.
Synthesized vast amounts of it through nuclear fusion and then through processes we call dredge up, mix that carbon up to its surface layers before puffing them off to form the nebula.
And that ejected material, that beautiful spirograph shell we see full of carbon,
will eventually disperse and mix with the interstellar gas and dust. It becomes the raw material for the next generation of stars, planets.
and potentially life. Absolutely. A huge fraction of the carbon in the universe. The carbon that forms the basis of all organic chemistry, the carbon in you and me, originated in stars that went through exactly this phase.
So tracing the carbon atoms in my hand back, many came from a star like IC418's progenitor.
That's the cosmic cycle. So when IC418 challenges our models of how these stars evolve and die, it directly challenges our understanding of how the ingredients essential for our existence were made and spread through the galaxy.
And the problem isn't just the heating speed, right? There was another major conflict with the models related to the star's mass.
Yes, this might be the most profound part. The study used observations of the nebula and the white dwarf to calculate the original mass of the star before it started shedding its layers.
The progenitor mass, what did they find?
They determined it was about 1.4 times the mass of our sun. So a bit heftier than the sun, but not dramatically so.
Okay, 1.4 solar masses. An empirical measurement based on the current system.
Right. Now here's the clash. Our standard stellar evolution models generally predict that a star needs to be significantly more massive to produce the amount of carbon enrichment we see in IC418.
How much more massive?
Often in the range of, say, 2.5 to 3 times the mass of the sun. The models suggested you needed that much more initial gravitational squeeze, that much more fuel to drive the nuclear reactions and the dredge-up processes efficiently enough to create such a carbon-rich outflow.
Hold on, so the actual star they measured was substantially smaller than the model said was necessary, yet it somehow produced all that carbon.
Exactly. It seems this 1.4 solar mass star was far more efficient at manufacturing and ejecting carbon than our standard models allowed for.
How could that happen? Does it change how we think about that dredge-up process?
It certainly suggests we need to revisit it. The third dredge-up is this complex process where convection currents deep inside the star bring freshly synthesized elements, like carbon, up to the surface layers. If a star of only 1.4 solar masses can do this so effectively, then either the minimum mass required for efficient dredge-up is lower than we thought, or the process itself is more efficient in stars of this size than the models currently simulate.
Either way, it means our fundamental understanding needs adjusting.
It's a major revision. If the threshold for being a significant carbon source is lower, well, think about it. There are many more stars born with around 1.4 solar masses than with 2.5 or 3 solar masses.
So it could dramatically increase the number of stars contributing to the galaxy's carbon budget.
Precisely. It potentially means the universe has been seeded with the building blocks of life much more widely by a larger population of stars than we previously calculated.
Wow, that's a huge implication stemming from observing one nebula carefully.
It's a classic case of a single, well-studied object potentially breaking a widely accepted model. And it really highlights the power of that long-term observational approach.
Tying it all together.
Absolutely. This mass discrepancy, this carbon puzzle, it only really comes into sharp focus when you combine the modern measurements with that full 130-year history. Without tracking its evolution, seeing that rapid, but not that rapid heating, confirming its stage of life, we wouldn't have the context to confidently challenge the mass models.
Which brings us back full circle to the value of those old archives, those dusty glass plates.
They're not just history, they're irreplaceable scientific data. They capture dynamics over timescales that no single modern mission, no matter how advanced, can replicate. You simply can't tell Hubble to wait 130 years.
We're relying on the meticulous work of astronomers from generations ago to refine 21st century astrophysics.
It's a powerful reminder. Sometimes the most cutting-edge science comes from combining the newest tools with the oldest records.
The source mentioned another great example, finding hints of planets around Van Manen's star.
Yes, in 2016, A potential planetary system, or at least debris, spotted entirely on a photographic plate taken way back in 1917. It sat in an archive for nearly a century.
Just waiting for someone to look at it with modern questions and techniques?
It proves these archives are potential gold mines. We need to value them, preserve them, digitize them. The 130-year story of IC418 is Exhibit A for why that's so critical.
Okay, let's quickly recap the key takeaways from this incredible story of the Spirograph Nebula, IC418. First, it's one of those super rare objects in the sky that actually visibly changes over a human lifetime. It shatters that idea of a static universe.
Definitely.
Yeah.
Second, by piecing together 130 years of data from handwritten notes and glass plates right up to Hubble, scientists tracked its central star heating up by a massive 3,000 degrees Celsius. That's achieving in just over a century what our sun took maybe 10 million years to do during its formation.
Right. And third, that heating rate, combined with the star's measured original mass of only 1.4 solar masses, throws a real wrench into our standard models.
The star's heating slower than predicted, and it produced way more carbon than models thought possible for a star that size.
Suggesting we need to rethink how efficiently stars make carbon and spread it through the galaxy, the very stuff we're made of.
It connects this distant nebula directly to our own origins, forcing a revision of fundamental cosmic chemistry.
So if 130-year-old glass plates and, careful notes scribbled down in the 1890s are still generating groundbreaking science today, science that makes us rethink the origins of carbon, the basis of life itself, it really makes you wonder, doesn't it?
It absolutely does.
What else might be hiding right now, undiscovered in dusty archives and old notebooks around the world? What breakthroughs are just waiting for the right person to connect those historical dots with modern analysis?
What revolutionary science are we sitting on, maybe unknowingly, right at this very moment?